So I'm Rohit. I'm working in AWI and performing the frontier simulations for EERIE for AWI and analyzing them. So today, so here what you are seeing is a snapshot of the ocean current at 50-meter depth in one of our simulations, confirming that we are having eddies. So that's the EERIE project. So first I wanted to start with showing you that the ocean eddies over the eddy-rich region over the North Atlantic. You can see the eddies. So what mainly I would like to go next is what is the model setup to give everyone an overview. What we are running here in AWI is the IFS Cycle 48R1 and TC1279 resolution, which is a 9-kilometer atmosphere. It's coupled with the FESOM ocean model from AWI, which has a minimal resolution of 5 kilometers. And what we did already, we had 5 years of ocean-only spin-up with EN4 boundary forcing, and then we did a couple spin-up for 50 years with that model. So we had that model. You can see the global mean temperature evolution during that spin-up process. You can see, maybe you remember of whom were earlier in EERIE, that our model showed a drift, went towards a colder temperature because of the Arctic region, and the Nordic seas were getting cold and ice was forming there. And then by the end of the simulations, luckily we found some comeback so some recovery of those cold drift. And for after 50 years of doing that, we started from there, currently doing a control simulations and a historical simulation. Both are in their 36th year right now, so then until 35th year is done. Although I think you all have right now data for 20 years. Today I am going to show you 10 more years included, 30 years, and hopefully you can all have 30 years this week or next week. We can make sure that it can happen. And then first, I wanted to show the global mean temperature evolution in that 30-year period of the control, and historical and comparison with the ERA 5, which shows that there is no surprises or sudden drifts anymore. They are going quite well in comparison with what we see in ERA 5. So there is still not a clear signal of the global warming yet in the historical simulation, which is also there in the ERA 5, but they're all in the similar range, roaming in the similar zone. If we want to see the global mean climate, so the yearly mean climatology of 2-meter temperature comparison, from the first look, you also don't see any surprises. It represents mostly exactly, they appear that as if they're the same. So they're doing quite well. But if you want to see the differences, so you can look at the bias figure, and then you can see that, okay, we have quite a good performance global 2-meter temperature wise over the globe, but in the polar regions now we have some warming over the Antarctic, and the Nordic seas cooling is still there. So left hand side you see the historical climatology difference, and the right hand side the control. So they both are present in both of them, so which is sign that we can use the control to separate this when we have the climate change happening in the signal. But we have this effect in the southern ocean and over the Antarctica. And if we separate two hemisphere temperature, we find that, of course, in the northern hemisphere, the highest temperature that we see in ERA 5, we are reaching quite well. Why in our model, the lowest temperature is a little bit low, so the winters are a little bit colder in the models. You can see in the bottom part, in the left-hand side is for the northern hemisphere, it's an average of from 20 north to 90 north. And for when we go to southern hemisphere, we see that in the summer, basically this warm signal that you have seen in the previous plot is basically happening in the summer. So the winter, we are having the temperature that we expect as we see, but in the summer, the temperatures are reaching much higher. So we had an understanding from the spin up. At the end of the spin up, we started losing our sea ice over the Weddell Sea. So first of all, we wanted to check that sea ice region. So here, a comparison in the summer period month, one of the months in February, climatology in our run, and you can see that the sea ices are kind of not staying in this region. So this sea ice was started to go off at the end of the spin up due to some reason which we still have to figure out, and that's kind of persistent. So every summer the sea ice kind of vanishes over this region. And you can see it in the time series here. Whenever the summer comes, the sea ice area almost reaching zero. Although you can see in the beginning of the run, when we started the control, sea ice was in the winter was also not as much as we expected from what we expect, but it caught up with time. We see that with the winter sea ice is kind of coming into what we expect, but with the summer we are consistently having this issue. But if we go forward and we want to look at the ocean eddies or the ocean circulations, so here you can see a comparison of the ocean circulations in our model, the climatology of the mean sea surface height, comparing with the AWI, and you can see the ocean circulation, general circulations are quite well represented. Of course, over the Gulf Stream or the subpolar gyre region has a bit higher intensity of the SSH in our model. But then if, as we are working with ocean eddies here, if we compare our ocean eddies with the AWI, we see that we very well represent the ocean eddies, eddy rich region. So this is the daily sea surface height standard deviation over the entire period, and you can see that they match quite well, except of course the Gulf Stream region, one of the most difficult regions to simulate properly usually, which we still have to, it's just still having a bit more zonal tendencies, but compared to AWI, but except that, most of the other regions we have quite good simulations. And then ENSO and its variability, if we want to look into the ENSO and its variability, we see that if in the first look, if you see, you might be confused which one is observation and which one is model. They're very similar in their patterns. So the variability associated with the ENSO over the globe is quite well simulated with their global footprint. It's also pretty well similar what we see, and then the ENSO variability is also coming very good. In the ERA 5 data I used, I have to check a little bit because there is SST range is a little bit suspicious. It's a bit more higher range in the HADI SST, so I have to check. So that this variability that you see for ERA 5 should be a little bit more compared to other, if we compare with other observed SST data. So we have to figure out what's happening. But the overall pattern of SST, and so now if I finally want to come to the overall performance, here you can see the overall performance of the historical simulations of these 30 years. So there is a lot of information here just to decode for your easiness. I want to say that the green, of course, means good, red means not good. So in general, you see more green here, and in the x-axis, we are moving from Arctic towards the Antarctic for different seasons. And the scores here basically are showing the scores compared to CMIP6 multimodal mean. So CMIP6 multimodal mean, whatever their performance, the bias in the CMIP6 multimodal mean compared to, if this is green, means we improved compared to that. So it's almost, the green regions are showing that whatever CMIP6 multimodal mean showed, we are in this run, it shows a better performance compared to that. And the red regions are showing there is some issues, and you can identify immediately that the end of the tail in the x-axis is Antarctic DJF, is Antarctic summer. You have all red. So basically what I have shown for the Antarctic. So that's kind of also reducing the all over score. So if the all over score is 1, then we are like similar to CMIP6. If it's getting lower than 1, then we are improved than what we have seen in CMIP6. So you can see other regions, mostly in the y-axis, we have atmosphere in the top, sea ice concentration, of course, at the top, but then after that, atmospheric parameters, and then we go towards the ocean parameters. You also see that the effect, maybe the Arctic sea ice is getting better, the sea ice concentration over the Arctic biases are getting reduced, as what I did previously for spin up, but its effect in the salinity and the temperature in the depth levels are having some effect. So you can see the 10-meter salinity, 10-meter depth salinity still having some biases. Basically, you see these biases over the Kara Sea and the Barents Sea, which I think it's still the after effect of that drift that we've seen in the spin up, which still needs time, but we need to confirm what. And mainly, except that the main other issue is the mean SST over the tropical El Nino region mean SST. The variability you have seen that we simulate quite well, but the mean SST is having bias, which also reflects in the 10-meter depth. But as you go deeper, the biases are not there. So we have a bias over the Nino region SST mean. And of course, Antarctic, and then the Arctic, and then the other region is this 100-meter depth, the tropical SSTs tropical temperatures. So tropical SSTs are having a bias. I don't know. We have to also investigate at the 100-meter depth in the ocean. The SSTs, not SSTs, the ocean temperatures are having a bias. But if you go further depth, it's all gone.
1 minute.
Okay. So now to summarize, so what I'm showing you here, 30 years of historical and control simulations. Hopefully we all can have a look at that by next week, this week or by next week. It's almost ready to be given. And you've seen that the global mean climate comparable to the reanalysis and the reduced cold drift on the northern high latitude as we have started in the spin up. But there is enhanced warming over the Antarctic and the parts of Southern ocean currents. Radioactivity is very close to what we see in the observations. INSO variability is well simulated. Overall performance shows improvement most part, except mainly the polar regions. So if the polar region starts getting green, the score might go to half, 0.5 or so, which would be really good compared to what we have seen before. So mainly we will try to investigate what's happening in the Antarctic in the summer ice, why it's going, what's happening here, why it's reaching zero. And estimated finish, I can see that if everything goes well, there's a supercomputing system and everything, then by the end of December, we might have the whole historical simulations, and hopefully you can all have we can all have a look by the time of our General Assembly in the whole historical simulations. Thank you.
Okay, thank you very much, Rohit.